Hi, this is Mrs. Kidman, and in this video, we are going to be going over what it means to have rational exponents. Now remember, rational numbers are numbers that we can write as a fraction. So what this really means is we're looking at exponents that are fractions. So let's take a look at some of those. Now, before we do, we're going to start by talking about nth roots. Now, the reason why we're going to talk about this is because of this property here. The nth root of a is the same as a to the 1 over n. So we can rewrite radicals or things to the nth root as a fractional exponent. And that becomes helpful if we're trying to combine things with exponents and radicals together. It also is helpful if we don't know what something is. So for example, I might know what the cubed root of 27 is, but I might not know what 27 to the 1/3 power is. But I could go back into that radical form and figure that out easily. So that's why we want to know both of those. So we can either combine exponents with radicals, or we can solve things to rational exponents. Now, when we're talking about the number of solutions or the number of roots with these, it's kind of unique. If our n is an odd number, so 3, 5, 7, 9, there's only going to be one solution with that. So for example, the cubed root of 8 is only going to be 2. It can't be -2, it has to be 2. Now if n is even, we have 3 options of what's going to happen depending on what a is. So if a is a positive number, so the number underneath, we have 2 real solutions, the positive and negative version of that solution. So think about it this way. The square root of 4, well, the square root of 4 is going to be 2, right? It can also be -2. The reason why it can be both is, think of this, 2 squared equals 4, and -2 squared also equals 4. So we're going to have 2 solutions here, the positive and negative version of whatever that is. If n is an even number and a equals 0, we're only going to have one solution. And guess what that solution is? That's right, 0, because 0 raised to any power other than 0 is always going to be 0. And then if n is even and a is less than 0, we're going to have no solutions. Because think of a negative number. I have to multiply an even number of negative numbers together to get it that way. If it's even and I have a negative number inside, so I have like the square root of -8, well, it's impossible for me to break this down. I get -2, 4, -2, 2, right? That doesn't come out as an even number there. -2, -2, I still end up with a negative inside my square root. So it's impossible for us to get a number with a real solution, okay? So if n is odd, there's one answer. If it's even and a is positive, so the number under the radical is positive, 2 solutions. If the number under the radical is 0, we have one answer. That answer is 0. And if it's a negative number underneath our radical, we have no solutions. So now let's take a look using this idea. So right here, I've got the cubed roots. 3, well, that's an odd number, so there's only going to be one solution here. So let me break it down. -2, 4, -2, -2. So what does that equal? That's going to equal -2. Now let's take a look at C here. 16 to the 1/4. Well, on that last page, I learned 16 to the 1/4 is the same as the 4th root of 16. And I can figure out what the 4th root of 16 is without a calculator. I can break it down, and I can see that the 4th root of 16 equals 2. But we also found out on that last page, if this 4 is an even number, which 4 is, we actually have 2 solutions, 2 and -2. And I challenge you to check that out. 2 to the 4th, well, that equals 16. And -2 to the 4th, well, that's also going to give us 16. Now, that's very different than this option D here, where we end up with the 4th root of -16. Now it's even, the number underneath is a negative, so we know that this has to have no real solutions. Now, if we want to break this down, we can try, and we get -2, 8, -2, -4, -2, 2. Notice it's impossible for us to get 4 of something, so we can't have a solution there. So there are no real solutions. We could simplify it, but we can't even simplify this. There is no solutions to this at all. So that's kind of what we're talking about with those roots. Now, looking at those rational exponents, we know n, the nth root of a, is the same as a to the 1n. Now that's great. But we also can look at these rational exponents where it's more than just a to the 1/nth. We can look at a to the n-nth, and that's actually the same as saying the nth root of a to the power of n. We could also write it as the nth root of a to the power of m, where m's on the inside of our radical. However, we're not really going to use this method in class. This is the one we want to use. The reason why is because this allows us to simplify that radical, just like we learned in the previous video. Simplify our radical and then put whatever that solution is to the power of n. So we're going to practice just rewriting these before we do anything else. So let's rewrite x to the 2/3. Now x to the 2/3, this bottom number here, that's going to be my nth root. And this top number here is what I'm going to put it to the power of. So here I am, I have a third root or a cubic root, and I'm going to put the cubic root of x, and I'm going to square it. There we go. Now, doing it in reverse, this tells me that I'm doing m, there's my power, to the root. So that's going to be m to the 3/7. Now we can rewrite these other ones as well. We're going to skip this w squared, but I want to look at this x to the 23rd times the 11th root. Now, if I were to break this down and I were to write all those x's, 23 x's, I'm not going to do that because that's a lot. But if I were to write 23 x's and then I circle those groups of 11, I would end up with 2 groups of 11 and a single x left over. So there's actually 2 ways I could write this. I could write this as x to the 23/11, which is the simplest way. But I could also write it as x squared times x to the 1/11 as well, because here's my x squared. I have 2 x's that I could pull out of my radical and then 1 x left over. Or I could write, so that means I could write it as 2 to the 1/11. This is the way that we're going to stick with it in class. These other ways do work, but we want to write it as that improper fraction. So now using this, let's evaluate some of these. So 16 to the 3/4. Well, 16 to the 3/4, this fourth is my root. This is my power. So let's take a look. We have the fourth root of 16 raised to the power of 3. Let's figure out what the fourth root of 16 is. 2, 8, 2, 4. Look, that's going to be 2. Now, is it just 2? No. 4 is an even number. 16 is positive. So that means we actually have 2 solutions here. It's either going to be 2 cubed or it's going to be negative 2 cubed. We have both the positive and negative version of that. And 2 cubed is 8, and negative 2 cubed is negative 8. So those are our 2 solutions there. Remember that numerator is our power, the fourth is our root. So the same thing, we can set this one up the same way, the cubed root of 27 to the power of 4. Well, I know the cubed root of 27 breaks down into being 3. Now we learned with that page before that because this 3 is odd, there's only one solution here, and that's going to be 3. So 3 to the 4th root and 3 to the 4th equals 81. And that's our only solution there. So that's how we would do it if we were evaluating those to the power. We also can evaluate with negative numbers. We can rewrite these depending on how we want to rewrite them. But what I want to look at is simplifying expressions with rational exponents. So we simplify them the same way that we would simplify something with an integer exponent. We follow the same rules, it just is fractions now. So for example, this one would be 3 times x to the 1/2 times 4 times x to the 2/3, right? That's what it would come out to be. So if we're multiplying those, I'm going to multiply my 3 and my 4, and that's going to give me 12. And then I get x to the 1/2 times x to the 2/3. Now the power of a product rule says I can actually rewrite that as 12 times x to the 1/2 times 2/3. So that's actually going to be 12 to the x times x to the 3/6, or 12 times x to the 1/2, right? So that is a great way to simplify it. We're using those same properties that we talked about in section 1.4 on properties of exponents. We can do the same thing here, but instead of adding our exponents, we would subtract them. We can look at a problem like this one, and we are going to use this example and actually go through it. So remember, our negative exponents go down, If the negative's on the bottom, it's going to go up. And so then we can solve that, and we can end up with x to the 3/2. This 2 is going to stay on the bottom here. X to the 3/2 times x to the 4th over 2 times y to the 5/2, y to the 1/4. And then we can just add those exponents using that property, and we will end up getting on top x to the 11/2 over 2 times y to the 11/4. So that's what we would end up getting there. Simple, just like we did before, but we're simplifying that. We can do that even with this -1/2 exponent. Remember, we would flip our fraction, we would take the square root of it. It's awesome. So that is kind of how you deal with those rational exponents. So again, they follow the same properties as our other exponents do. So we still have that property that anything to the power of 0 is 1. If it's negative, then we rewrite it as 1 over that value. If they have the same base, we can still add the exponents. If we're dividing numbers with the same base, we can still subtract our exponents. We can follow all of those same properties. So as we look at these, go ahead and get started on your assignment, which is a worksheet called Rational Exponents and Radicals. So check that out, and hopefully if you have any questions, you will reach out.